In this video, we're going to explore some more uses for the ideal gas law. And so one of the other ways that we can use the ideal gas law, other than just tracking parameters or figuring out how many moles there are, can be used to find the density of gases. Now, to find the density of any gas, what we need are the molar mass of that gas and its molar volume. And with gases, density is going to have units of grams per liter because, again, gases are considerably less dense. They take up far more space than liquids or solids. So the approach that we're going to take here to find density is we're going to use our measurements to figure out what the mass is, and then using the ideal gas law and this manipulation of the ideal gas law, V is equal to nRT over P, we should be able to determine the volume. And so mass divided by volume, that's going to give us density. So let's take a look at an example of this kind of problem. Now this kind of problem is actually going to ask us to go in the reverse. We're given a density, 1.83 grams per liter. We're given some pressure and temperature conditions. What we need to know is, well, what is the molar mass and the identity of this gas that comes when nitric acid and sodium bicarbonate mix together? So if we take it on from this perspective, using density again, we have 1.83 grams of gas divided by 1 liter of gas. That's our density. That's what we've been given. Now, we also, from this information, know that this 1 liter of gas is also at 1 atmosphere of pressure and 23 degrees Celsius of temperature. So, using the ideal gas law, where PV is equal to nRT, if we rearrange that, N, number of moles, is equal to PV over RT. So if we take it from this approach, our pressure is 1 atmosphere. Our volume is 1 liter. Our gas constants, 0.08206 liter atmospheres per mole Kelvin. And our temperature, 23 degrees Celsius, is 296 Kelvin. So we do our maneuvering, liters cancel, atmospheres cancel, Kelvin cancel. I'm left over with 1 over 1 over moles. So I'm going to get moles out of this. Throw in my trusty calculator here. 1 divided by 0.08206 divided by 296. And we get 0.0411, or excuse me, 0.04012 moles of gas. So remember, for molar mass, I need mass of gas divided by moles of gas. I now have both. My mass of gas was 1.83 grams, and my moles of gas, 0.0412 moles. And if I do that calculation, 1.83 divided by 0.0412, I get 44.4 grams per mole. Okay, now that gives us the molar mass. What do we do about this identity thing? Well, that's where we have to know how to handle these kinds of reactions. And this is a double replacement reaction. HNO3 reacts with sodium bicarbonate to make, in a double replacement reaction, sodium nitrate, NaNO3. And if I put it together, I would get H2CO3, carbonic acid. Now, hopefully you've picked up on this by this point. Carbonic acid does not ever form as a product. In fact, whenever we see it as a product, we need to immediately think to ourselves, that's not right. It spontaneously decomposes into water and carbon dioxide. And so this is our balanced chemical equation. Now, of these products, we're looking for a gas, so we can automatically eliminate the sodium nitrate from contention there. It's either water or carbon dioxide. Water has a mass of 18.02. Carbon dioxide has a mass of 44.01. That's a lot closer, and so our mystery gas must be the carbon dioxide in this case. So density and calculations along those lines are another way that we can use the ideal gas law. Another way is in stoichiometry. Now in stoichiometry, we can use the ideal gas law by keeping in mind that if I know pressure, volume, and temperature, the ideal gas law tells me that I can convert to knowing the number of moles. And remember, anything that we can do to figure out the number of moles of a substance can immediately be used in a stoichiometry kind of sense. And so you may recall this particular diagram from back in chapter 7, and we've added pieces to this along the way. We're going to add another piece to it right now, and that piece is, what if I know the volume of whatever substance A is in its gas phase? Or what if I'm trying to find the volume of a gas for substance B? Well, now that we have the ideal gas law to draw upon, this is not actually as difficult of a calculation step as one might think. To go from volume to moles, I either need to use one form of the ideal gas law, manipulated, or the other form of the ideal gas law, depending upon what it is I'm trying to do. And the same would be true on the other side. If I need volume from moles, I take the moles times the gas constant times temperature divided by the pressure, and I can find volume. If I have volume and I'm trying to find moles, I can go that way just as easily. And so to this end, we can do some interesting kinds of calculations involving stoichiometry and stoichiometric kinds of manipulations. Let's take a look at an example. So here's the reaction that takes place in car airbags. Car airbags are filled with a substance called sodium azide, and when your car goes through a sudden change of direction or stop, that causes the spark to happen inside the airbag. It spontaneously ignites, and ignites with a heavy amount of nitrogen gas. The question is this: how many grams of sodium azide do I need to put in those airbags if I was going to sufficiently fill an airbag of these dimensions to these conditions? Now, a little bit of housekeeping before we get into this too much. A 48 by 48 by 25 bag would be 57,600 cubic centimeters. Remember that cubic centimeters are the same thing as milliliters. And so we could very quickly turn that into liters just by doing that calculation conversion. Now the question is, I have this volume and this pressure and this temperature. How many moles of nitrogen is that? And once I know the moles of nitrogen, can I turn that into moles and then grams of sodium azide? And the answer is, yeah, of course. I just need to know what to do. So N is equal to PV over RT. So my pressure is 1.20 atmospheres. My volume is 57.6 liters. And I'm going to divide that by R, 8206 liter atmospheres per mole Kelvin. And my Kelvin temperature, 15 degrees, would be 288 Kelvin. So put all of that in, cross out all of my extra units. I should be left with just 1 over moles, or moles. Get my calculator back out. 1.20 times 57.6 divided by 0.08206 divided by 288. And we got ourselves 2.92 moles of nitrogen. Now, stoichiometry takes us the rest of the way here. 2.92 moles of nitrogen. I know based on my balanced chemical equation that for every 3 moles of nitrogen, I get 2 moles of sodium azide. And in my last step, 1 mole of sodium azide is 22.99 plus 14.01 times 3, 65.02 grams. And so calculator out again, 2.92 multiplied by 2 multiplied by 65.02 divided by 3. To 3 significant figures, I need 127 grams of sodium azide, which is not an insignificant amount at all. So the moral of the story here with regard to the ideal gas law and this particular application in stoichiometry is it's all more of the same. If you remember how to use this map to organize your thoughts, and you just remember that the ideal gas law is the thing that bridges you between bridges you between volume, pressure, and temperature of a gas and moles of a gas, then all that this is just another application, just like what we saw in Chapter 8, when we had to use molarity to go between moles of substance, moles of solute, and liters of solution. It's the same kind of thing. So we've got one more video in this series. We're going to talk about Dalton's law of partial pressures in the next video. Until then, have a good day.